Hello there. So, we have been talking about free vibration, and again in this lecture also I shall continue to talk about free vibration of multi-degree of freedom structures or systems. Okay? So, let us look at this thing. Let us start by looking at what we have already stated, and that is essentially we need to solve this equation. Okay? So, let us start by looking at a problem that we have in a way looked at earlier, and that is, let me take the rigid bar. In this lecture, what I am going to be doing is, up till now I have been talking in abstraction. I have been saying solve this, this is how it, then how you get it. Now, I have not talked about how you solve it. Okay? And that is a very, very important part of the entire procedure. Okay? So, now, let us start by taking a simple problem. M bar, note that this is not allowed to move in this direction. Okay? And I will call this k, and right now I will call this k, I will develop 2k one later on. Let us start with k. Okay, we remember we had done k and 2k over here, okay, and we had defined the degrees of freedom 1 at this u x and u theta. So, let us see with v as u x and u theta, and again I have already derived the mass matrix. The mass matrix looks like this. And I am going to use a specific, I am going to say m is equal to m bar L. That is the total mass of bar. Okay? I am going to use this. So, if you look at it, m bar L, okay, and so therefore, m bar L becomes m, okay, this is 0, 0, bar L cubed by 12. So, it becomes m L squared by 12. Okay. And you can derive k the way we have derived it. In this particular case, it turns out to be 2k 0 0. You can derive k I j the way I have derived. I am not going to go into deriving this thing at every point. Okay. So, this is my k. Okay. So, now I have got my m and k. So, what I need to do is write down this k minus omega squared m. So, this is going to be equal to 2k minus omega squared m, then 0 0, because these are both 0, this is also 0. So, this is 0, and I have k L squared by 2 minus m L squared by 12 into, so this is equal to this. So, this into phi is equal to 0 is the solution that I need to do. Okay. So, how do I do that? Well, remember that for us to do that, so I am going to rewrite this here. 2 k minus omega squared 0 0 k L squared by 2 minus m L squared by 12 phi is equal to 0. So, obviously, determinant of this matrix is equal to 0. And so, what is the determinant? Determinant is equal to 2 k minus m omega squared into k L squared by 2 m L squared by 12 minus 0, okay, and this is the determinant, that is equal to 0. That is what we are given, that for this to be valid, the determinant of this has to be 0. So, which basically implies that 2 k minus omega squared m into k L squared by 2 m L squared by 12 is equal to 0. Now, note these are factors. So, what does that mean? It means that I have two values. So, let me just write it down first. Okay. This one gives me what? 2 k minus m is equal to 0, and this gives me k L squared by 2 and m L squared by 12 is equal. So, there are two possibilities. This could be 0 or this could be 0. So, if this is 0, then this is what happens, and so therefore, omega 1 squared is equal to 2 k upon m, and over here, sorry, this is oh my god, omega squared, omega squared, omega squared, omega squared. So, from this I get omega 2 squared is equal to k L squared upon 2 upon this. So, this becomes 6 k over m. So, if this is equal to 0, then for this to be 0, omega has to be equal to 6 k by m, and for this to be 0, omega has to be equal to 2 k by m. So, now, what are my natural frequencies? My natural frequencies, and note that this natural is indeed the lowest frequency. So, this is equal to square root upon 2 k by m, and this one is indeed the higher frequency, which is 6 k by m. Note, fundamental, that this problem has two frequencies. It is a 2 degree of freedom. It has two frequencies, both are positive and both are distinct from each other. One is root k root upon 2 k upon m, and the other one is root 6 k upon m. What is the next step? The next step in this, so I find out the frequencies. So, the determinant that is equal to 0 is known as the frequency equation. So, we solve the frequency equation to get the frequencies. So, we have got the frequencies. Now, next what? Well, for each frequency, I need to find out its mode shape. How do I do that? Well, the way I do it is the following. I have got this, right. So, what I have is k minus omega squared m into phi 1 is equal to 0, and I have k minus omega 2 squared m phi 2 is equal to 0. Okay. So, the first one I plug in omega 1 squared, I plug in omega 1 squared in here. So, if you plug in omega 1 squared in here, what do I get? Well, let us see, let me put it. So, 2 k minus omega 1 is 2 k upon m into m, okay, 0, 0, and this one is what? It is equal to k L squared upon 2 minus 2 k by m into m L squared by 12 Okay. And here phi 1. So, this is phi 1, phi 2, and this is the first mode shape is equal to 0, 0. Plug it in here, what do you get? This becomes 0, 0, and the bottom one becomes 0, this one. And what is this one? M cancels. Okay, so this becomes k l squared upon 6, and if you do k l squared upon 6, this becomes k l squared upon 3. K l squared upon 2 minus k l squared upon 6 is nothing but k l squared upon 3. Okay. What does the first equation give you? 0 into phi 1 plus 0 into phi 2 is 0. Well, obvious. It is a trivial solution. We get nothing from phi 1 and phi 2. What does the second one give you? The second one gives you that k l squared 3 into phi 2, 0 phi 1 plus k l squared phi 2 of 1 is equal to 0. So, what does that mean? This implies that phi 2 of 1 is equal to 0. Well, we know that is equal to 0. So, what is phi 1? Well, you know, everything is in terms of phi 1. Remember, I said that you can't find out any one of them. Okay. So, therefore, in this particular case, for want of better thing, I take it equal to 1. So, that means I have found out omega 1. Omega 1 is square root of 2k upon m, and phi 1 is equal to 1, 0. Okay. Now, this is not orthonormal, it is just a mode shape. Okay. Let us look at plug in omega 2. Omega 2 is, so therefore, I have this 2k minus 6k upon m into m 0, 0, k l squared upon 2 minus 6k upon m into m l squared by 12, and this is the second mode. So, this is the first and second of the second mode, and this is equal to 0, 0. Look at the first equation. What does it say? So, this becomes equal to minus 4k 0, 0, and look at this 6k m cancel, 6 upon 12 k l squared by 2, k l squared by 2 is 0. What does the first equation tell me? That phi 1 2 is equal to 0. And what is phi 2 2? Well, the second equation does not give me phi 2 2 is equal to 1. So, that means, if you look at this, omega 2 is equal to square root 6 upon m, phi 2 is equal to 0, 1. Now, let us look at what these mean. Now, first of all, let me try to see if these are orthogonal with respect to each other. Well, let us see, are they mass orthogonal? Well, let us put it in 1 0 into the mass. Mass is what? Mass matrix is m 0 0 m l squared by 12 into 0 1, right. 1 0 is phi 1. So, it is phi 1 transpose m into phi 2. Okay. So, if you look at this, this one gives me what? This is equal to 1 0 0 into 0. So, this is 0. This is 0 into 0 into m l squared by 12. Now, do 1 into 0 is 0. Check. Orthogonality done. Okay. So, orthogonality function is Done. Now, next what is it? Well, what's the next step? Well, let's draw what these look like. Let's draw them. And if I draw them, let's see what it looks like. Omega 1, 2k by m, phi 1 is 1, 0. That means ux equal to 1 and u theta is equal to 0. What a kind of mode shape is that? This. That means the vibration is in this fashion, that this is the starting, it goes here, comes down, goes here, comes down, exactly laterally. This is what it does. Okay? This is how the vibration of free vibration of this is. Okay? And omega 2, which is 6k upon m, phi 2 is equal to 0, 1. Now, ux is equal to 0, u theta is equal to 1. What kind of a movement is that? So, this one is like 1, 1 and this one is like L over 2, L over 2. But if you look at L over 2, what does that mean? This we can also say that all that means is that if this is unity, these are L by 2. Okay. But so that means what kind of a vibration are we looking at? About the center, it's going to do this only. So, the center is. So, you see, remember I had solved a problem which was like this, single degree of freedom with this at the center, and we got that this is the only degree of freedom. Do you see this? That this looks like that degree of freedom, doesn't it? It's only rotating about the center. So, that's the second mode. This, note that lower frequency is a lower energy mode. This is the easiest thing for it to do, vibrate. Higher frequency, higher energy. You know, the two springs are being rotated in opposite direction. That's a much higher frequency mode. Okay? So, it has a higher frequency. So, that's the point. The reason why we put the lowest, you know, there is a reason why we have ordered it where the lowest frequency is the first frequency, and as you go up, you get an increasing order. The reason behind it is that the fundamental, this is the fundamental mode of vibration. See, all structures are as lazy as we are. Okay? And that is the reason why a structure, if allowed to vibrate by itself, it will always vibrate in the fundamental mode, because that is the lowest frequency mode that you have. Okay? Higher frequencies are associated with higher strain energies, higher energy mode. It's difficult to do this. Okay? So, it would rather not do that. Okay? So, that is the reason why the fundamental mode, it is called the fundamental mode. Why is it called fundamental? Fundamental because left to itself, completely left to itself, not being subjected to any kind of random motion. Okay, left to itself, it will always, and if you just hit it, okay, ultimately it will just try to vibrate in this fashion. This particular structure will try to vibrate only in this way. So, that is called the fundamental mode of vibration. The fundamental mode of vibration has a frequency associated with it and a shape associated with it. Okay? So, you understand what the shape means? The shape is not some numbers, it actually means how does the structure vibrate. Okay? So, now let us look at this particular same problem. Let us look at this problem, and let me solve this problem using another degree of freedom, using two other degrees of freedom. Remember, we did that. Okay? These were defined at the geometric center. Now, I am going to write this, the same problem, exactly the same problem, with mass m. Now, I am saying the mass is uniformly distributed, total mass is m, okay, which is equal to m bar L. Okay. This is k, this is k, and my degrees of freedom are defined as V1 and V2. Okay. Now, again I am not going to go into the details. We have already evaluated the mass matrix for V1 and V2, and the mass matrix looks like this: m by 3, it's m bar L by 3 if you remember. So, that I have said is m, okay, m by 6, m by 3. I am just using m as easier than m bar L, that is all. It is not as if there is a mass and that is why I am putting m. It is just that it is m bar L, so I am just replacing it, just for writing it is easier. The k vector you will see just like the way we evaluated it is this. Okay. So, now corresponding to V, these are the mass and stiffness matrix. They look completely different from the mass and stiffness matrix corresponding to the degrees of freedom V x and V theta defined at the geometric center, completely different. So, I have stated this over and over again that the your mass and stiffness and load, this I am doing free vibration here, so there is no load. Okay. All of them depend on what? They depend on the degree of freedom, the way you define the degree of freedom. Okay. But now let us look at the free vibration. So, here I am going to do k minus omega squared m into phi is equal to 0. I am going to do this. So, if I do this, what does it become? It becomes k minus omega squared m by 3 and now 0 into omega squared m by 6, then 0 minus omega squared m by 6 and finally k into omega squared m by 3. This into phi is equal to 0. So, determinant is nothing but k minus omega squared m by 3 squared minus this is the determinant. The determinant is this into this minus this into this, right. I mean, I am not going to find that out. Okay. So, now let us see what this comes out to be equal to. This turns out to be equal to k squared minus 2 m k by 3 plus omega fourth m squared by 9 minus omega fourth m squared by 36 equal to 0. So, therefore, if this is there, see this is 1 upon 9, 1 upon 36. So, if you take 36 below 4 and minus 1. So, that is 3 upon 36, that is 12th. So, basically this equation then becomes nothing but the following: omega fourth m squared upon 12 minus 2 m k by 3 plus k squared is equal to 0. Now, I am going to multiply both sides by 12. So, then this becomes W L fourth m squared and then 12 comes here. So, that is 4. So, that becomes 8 m k plus 12 k squared is equal to 0, because 12 into 0 is still 0. Okay. So, now if you look at this, this will you can factorize it. Okay. 6 into 2 6. So, this becomes factorized as omega squared m minus 2 k and omega squared m into 6k. See that this becomes 12k and this becomes 2k, sorry, there is a omega, there is a omega squared here. This is omega squared here, omega squared 2mk upon 3. I always forget that. So, this is omega squared. So, if you do that, then this becomes 2m omega squared mk 6k, so you get this is equal to 0. This means that either this or this. So, if this is equal to 0, omega 1 squared is equal to 2k by m, omega 2 squared is equal to 6k by m. Note that both the frequencies are identical. Whether we used Vx, V theta or we used V1 and V2, we got exactly the same expression. Okay? And that is very, very interesting. Okay? So, therefore, remember I said that the frequencies are invariant. They do not depend on the way we define our degree of freedom, and this has been conclusively proved. We have used two m's, 2k's completely different. When you find out the eigenvalue, you get omega 1 squared is equal to 2k by m, omega 2 squared is equal to 6k by m, irrespective of any of the methods that you have chosen to do. Okay. Now, let us look further. Let us try to find out the frequencies. I mean, sorry, the mode shapes. How do I find out the mode shape? Well, I plug in k minus omega 1 squared m by 3, 0, omega 1 squared m by 6, 0 minus omega m by 6, k minus omega 1 squared m by 3 into phi 1 is equal to 0. And now phi 1 is given by phi 1, phi 2, 1. Okay. And so, therefore, if you look at this, what do you get? Well, let us see. Put in omega 1 squared. Omega 1 squared is 2k by m. 2k by m cancelled 2k. So, this becomes k by 3. Omega 1 squared 2k by m. So, this becomes minus k by 3. Similarly, this becomes minus k by 3 and this becomes k by 3. Phi 1, phi 2, 1. So, the first equation says that k 3 phi 1 1 minus k by 3 phi 2 1 is equal to 0, and the lower equation gives minus k by 3 phi 1 1 plus k by 3 phi 2 1 is equal to 0. Both of them give that phi 1 1 is equal to phi 2 1. That is all they give. So, what does that mean? My phi 1 is equal to, if I take phi 1 1 as 1, my phi 2 1 is also 1. That is all that means. So, that is the mode shape corresponding to 2k by m. Okay. And the second one, we will see what this looks like. You know, the mode shape looks very different. The other one you got 1 0. So, why? Well, we will see. The mode shape as it is given looks is dependent on the degrees of freedom, because here it is V 1 and V 2. Okay. So, therefore, but let us go back and try to solve the second one. The second one will give what? K minus omega 2 squared m by 3, 0 minus omega 2 squared m by 6, 0 minus omega 2 squared m upon 6, okay, k minus omega 2 squared m by 3 into phi 2 is equal to 0. Okay. Now, phi 2 is phi 1, phi 2 of second mode. This is corresponding to V1, this is corresponding to V2. Okay? And so, therefore, if we put in omega 2 squared is equal to 6k by m, if we plug it in, let us see what we get. You plug in 6k by m, 6k by m. So, 6k here, m cancel, 6k, this is 6 2. So, this becomes minus k. Okay. Here 6k, okay, upon m by m into 6 is minus k. Similarly, this is minus k, this is minus k. Phi 1, phi 2 of 2 is equal to 0 0. The first equation gives what? Minus k phi 1 2 minus k phi 2 2 is equal to 0. The second equation gives phi 1 2 minus k phi 2 2 is equal to 0. Both are identical. You see, this is a rank 2 matrix, you know, the m and k, okay. But because the determinant was put equal to 0, you see what does the rank become? N minus 1. So, it becomes a rank 1 matrix. What does that mean? There is only one independent equation. Both equations say the same thing. So, if I put it in, what does it say? It says that phi 1 1 is equal to minus phi 2 1. So, what is phi 2? Well, if I put this as 1, this I get as minus 1. Okay? Or if I put this as minus 1, I get this as plus 1. It does not matter. You know, you can choose any one of them to be 1 and choose the other one to be the other, whatever the relationship gives you. Okay? So, let us now look at these mode shapes. It's going to be very, very interesting. Omega 1 squared 2k by m, this is exactly the same. And let us look at what is the mode. The first mode says 1 1. Right? What does that mean? 1 1. What is the mode shape? See this? And that is the beauty. Okay? You know, even though the phis don't look the same, they actually are the same. It's going like this. Okay? What does omega 2 squared say? Omega 2 squared 6k upon m. If I do it, plus 1 minus 1. Plus 1 minus 1. Draw it, what do you get? 0 at the center. What kind of this thing is it? It's exactly the same as what we got earlier. And that, my friends, is what it is. The property matrices, the M and K, the mass matrix, stiffness matrix and the load, they are corresponding to a specific vector V. So, if you define your V differently, see I have it's on the same problem, I have taken, it is a 2 degree of freedom. So, I can choose any 2 independent degrees of freedom as long as I do that, it is fine. So, I chose first the one as Vx and V theta as the 2 degrees of freedom. Okay. Mass matrix was completely different from when I chose V1 and V2. Even the K matrix was completely different, but then when I solved the eigenvalue problem and found out the frequencies and mode shapes, both of them gave the same omega 1, same omega 2 and the same shapes. And this is what I mean by shape. Mode shape is not the specific phi that you get. Phi corresponds to a V. The values of phi correspond to a V. Now, you may say, well, this one is not the same. The other one was L by 2 and minus L by 2. Again, it is a factor. Okay. So, you know, this is what I said at the beginning. I could have chosen this as L upon 2 and this would become minus L upon 2 and I would get exactly the same thing. It is a shape. The values themselves do not matter. It is only when you get the orthonormal mode does it matter. Okay? Will they give the same result. Okay? And so that's essentially what you get out of this. Okay. So therefore, the mode shape and the thing are properties of the structure. Given a structure, the frequencies, the natural frequencies and mode shapes of vibrations are independent of how you define your degrees of freedom. Okay? And here, let me show something else. Okay? I have got 1, 1 and 1 minus 1, and let us see if its mass orthogonal and stiffness orthogonal. Well, they would be, right, because they are the same shape, but let us just go through the process. The process is phi 1 is equal to 1, 1. What is the mass matrix? Mass matrix is m by 3, m by 6, m by 6, m by 3, and phi 2. So, it is phi 1 transpose m phi 2. Okay. Phi 2 is 1 minus 1. Okay, so, let us see what happens. Let me do this thing first. It is m by 3 minus m by 6. So, this becomes 1, 1, and this becomes m by 3 minus m by 6 is what? M by 6. So, this becomes m by 6. Similarly, this is m by 6 minus m by 3, this becomes minus m by 6. If you do this, this becomes m by 6 minus m by 6, 0. So, orthogonality is obtained. Okay. Now, okay, I want to start off and say, remember I told you that if I use orthonormal mode shapes, you will get, and similarly, okay, by the way, I did not do the stiffness orthogonality. Let me do the stiffness orthogonality. What is the stiffness matrix in this particular case? It is equal to, so this is 1, 1, and stiffness matrix is k 0, 0, k 1 minus 1. So, this becomes k, this one becomes minus k, 1, 1 is equal to k minus k is equal to 0. So, all orthogonality is maintained. Now I want to go back and I want to look at the fact that, remember, let us define this. When I define V x and V theta, my mass matrix was m 0, 0, m L squared by 12, okay, and my phi 1 that I got was 1, 0, and the phi 2 that I got was 0, 1. Okay. When I chose V 1 and V 2, the two extreme displacements, my M matrix was m by 3, m by 6, m by 6, m by 3, and my phi 1 was 1, 1, phi 2 was minus 1, 1. Okay. So, let us see whether I can generate orthonormal mode shapes. So, what do I do? Well, I actually do phi 1 transpose m phi 1 and find out m 1. So, let me do it for the first one. If I do it for the first one, what do I get? I get the following. I get 1, 0 into m 0, 0 m L squared by 12 and 1, 0. Phi 1 transpose m phi 1. Okay. So, let me see what this gives me, 1, 0, and from the top I get m. So, I take m, the bottom one 0 into 0, 0. So, what do I get? 1, I get m. So, my m 1 is m. Okay. So, what do I need to do? Well, my orthonormal mode shape would be 1 upon square root of m 1 0. That is my orthonormal mode shape. Okay? And similarly, my orthonormal second mode shape would be what? Well, let us see. It is 0 1, that is phi 2 transpose into m. So, that is m 0 0 m l squared by 12 1 0, okay. Sorry, 0 1, that is phi 2 transpose m phi 2. So, if I look at this, this becomes 0 1, here this becomes 0 into 0. So, the top is 0 0 into 1, this becomes m l squared by 12. So, if I do this, my m 2 is equal to m l squared by 12. So, what do I need to do? Square root. So, my phi 2 transpose turns out to be equal to 12 upon m l squared square root 0 1. Okay? That is my orthonormal mode shape. Okay? I am not going to so I have just proved it to you and shown it to you, and I am not going to go into any of this. The other one you can do yourself and find out. Okay? I am going to now look at, you see, I have solved a problem in which the frequency equation could be factorized. So, that I actually got omega squared minus 2 k upon m into omega squared minus 6 k upon m is equal to 0. So, the factors themselves, if I can factorize it, I have got my omega. Well, the reason why I could factorize it was because that when I developed in terms of this thing, this is actually what is known as a symmetric system. It is a symmetric system. So, that the lateral displacement and the rotational displacement are uncoupled from each other, and therefore, I could factorize it. Let me take another problem in which I can't do that. Okay? And so, therefore, I go back to that original problem that we had solved in the thing, and that was that m bar, of course, this was k and this was 2k. Remember that problem? And that was a problem that we solved a few lectures ago, and the M matrix came out to be equal to M. M bar L is M, remember that. I keep repeating that. 0 0 m bar L cubed. So, that becomes m L squared, okay. And k, look back at your k matrix, you will say it is equal to 3 k, k L by 2, k L by 2, 3 k L squared by 4. Okay. So, these were the property matrices that we got corresponding to Vx and V theta. So, V was equal to Vx and V theta defined at the centroid. Okay. So, that was what we got. Okay. So, now let us solve this problem. Let us solve the eigenvalue problem. Okay. So, if we solve the eigenvalue problem, this is what you get. K minus omega squared m. So, this becomes k, k is 3 k minus omega squared m. So, here this is k L by 2 minus omega squared 0. This is k L by 2 minus omega squared 0, and this is 3 k L squared upon 4 minus omega squared m L squared by 12. This into phi is equal to 0. This implies that determinant of this is equal to 0, and the determinant is equal to 3 k minus omega squared m into 3k L squared upon 4 minus omega squared ml squared upon 12 minus this is 0 0. So, this becomes minus k L squared equal to 0. Okay. So, now let me expand this. If I expand this, what do I get? I get 9 k squared L squared upon 4, okay, minus omega squared m L squared upon 12 into 3k. Okay. Then I have minus omega squared m into 3k L squared by 4, and then finally plus omega fourth m squared L squared upon 12 minus k squared L squared upon 4, okay, is equal to 0. So, here if you look at this, 9 upon 4 minus 1 upon 4 becomes 2k L squared, 2k squared L squared. The omega squared terms you will see is 3 upon is m L squared upon 4. This is minus 3 by 4 k m k L squared. So, minus 1 by 4 minus 3 by 4 becomes minus 1. So, this becomes omega m squared, okay, m k L squared, okay, these two added, and then plus omega fourth m squared L squared upon 12 equal to 0. Now, what I am going to do is I am going to take the entire I am going to pre-multiply both sides by 12. Okay. So, if I do that, this becomes finally the equation, frequency equation is omega fourth m squared L squared minus 12 omega squared m k L squared plus 24 k squared L squared is equal to 0. Okay. Now, you see L squared is there in every one of them. So, I can actually put L squared outside and then take it on the other side. So, L squared disappears. So, the equation then essentially becomes the following. The equation, the frequency equation essentially becomes the following. It becomes minus 12 omega squared m k plus 24 k squared is equal to 0. Now, this cannot be factored. Okay, you can see it. I mean, factorization is a standard thing, but we can solve for omega squared, right? This is like a squared omega to the power, a omega to the power of fourth minus b omega squared plus c is equal to 0. Okay. So, my a is m squared, okay. My b is minus 12 m k, my c is 24 k squared. So, omega squared, which is a basic quantity, because omega fourth is omega squared squared. So, there is a quadratic in omega squared. So, omega squared is equal to 12 m k upon 2a. So, that is 2 m squared plus or minus 1 upon 2 m squared square root b squared. So, that becomes 144 m squared k squared minus 4 a c. 4 a c is 196 m squared k squared. So, this one, if you look at it, becomes essentially 48. okay, and 48 is 2 square root this thing. So, this becomes, by rewriting this becomes 6 k upon m plus minus m squared k squared also comes out as m k. Okay. So, what we are left with is plus minus k upon m into square root of 12. So, these are my omega squared that I get. So, if I solve for this, what do I get? I get omega 1 squared is equal to 6 minus root 12 into k by m. Omega 2 squared is equal to 6 plus root 12, obviously, right. And if you do this, this becomes equal to 2.596 k upon m, and this one becomes 9.464 k upon m. So, omega 1 is equal to square root of 2.596 root k upon m, and omega 2 is equal to square root of 9.464 square root of root upon k. Obviously, this is the lower one, this is the higher one. Okay. So, what I have shown is that, you know, every time, you see this is a 2 degree of freedom. So, in what you do is 2 degree of freedom, the frequency equation will be a quadratic in omega squared. If I have 3 degrees of freedom, the frequency equation will be a cubic in omega squared. Okay. So, if I take omega squared as lambda, what I have is, I have ultimately, now by the way, I am not going to go into the details of finding out phi 1 and phi 2. I have just shown you that I have just tried to evaluate omega 1 and omega 2 in a situation where you have you do not have a factorization. So, you have to solve the quadratic, okay, and quadratic solutions are closed form solutions. So, I have got those. Okay. The question then becomes is that, you see, when I take the determinant of k minus omega squared m is equal to 0, what you generate is a frequency equation, which is a function. Now, I will call this as lambda. Okay. So, it is a function of lambda is equal to 0, and this is a polynomial. And the order of the polynomial is really lambda to the power of n, where n is the degrees of freedom. Okay. So, you are actually solving a polynomial. Okay. You are finding out this basically becomes nothing but what? It becomes finding out the roots of a polynomial. Okay. In other words, what we are actually doing is, if you look at it pictorially what we are doing is a polynomial function, okay, in the 0, in the lambda space. Okay. What it happens is, what you are doing is something like this. At 0, this is always 0. I mean, you know, you do this, and what you are doing is you are finding out the roots. You are finding out this is f lambda. You are finding out the roots where f lambda is equal to 0. And what we are saying is that this is a polynomial of order n. So, therefore, there are going to be n roots. So, if it is 4 degrees of freedom, there will be 4 roots. And these 4 roots, this one is omega 1 squared, this one is omega 2 squared, this one is omega 3 squared, this one is omega 4 squared. This is the way. So, in a sense, you know, the from the determinant you get a polynomial, and it's the frequency, getting the frequencies of is just nothing but a root finding technique. So, numerically it is nothing but a root finding technique, and root finding techniques, there are many root finding numerical root finding techniques. So, if I have n degrees of freedom, I can always find out the n roots, and I know that since k and m are positive, definite and symmetric, that all the roots will lie in the positive lambda plane, that I know, and they will be all distinct. Okay. So, this in a sense is free vibration in its overview. Okay. Next time I will introduce you to a couple of basic types of problems, and then we will look at how to do response analysis of multi degree of freedom problems. Okay. Thank you. Bye bye.